How do we get this to point? The middle one, okay. There it is, okay. All right, so first of all, of course, let me thank the organizers for another opportunity to come talk in one of these wonderful workshops that have been coming out regularly here at IFT through ICTP. And well, this talk is going to be a little bit different from some of the subjects that I've been giving in these past opportunities. Usually I've been talking about thermoelectrics in general. This is going to be more of a workhorse type research, that something that's been going on through my career for the past 15 years or so. And so again, thanks for the opportunity to relive some of the interesting things that I've been doing in these past few times. You made me read some papers that I wrote like 15 years ago, and it's nice to go and revisit them. So the topic here is going to be what we've been discovering and of interesting ground state properties in general that came out in this rare earth nickel silicon 3 series. This is going to be more of a show and tell type presentation, like a colloquium rather than a workshop one. So I'm just going to basically go through historically what we've been doing. So it starts out with the Erbium System together with the nickel germanide one that forms a strongly correlated electron system, was the first one that we found out. So basically I could say that we're in the business of designing and discovering new compounds and then characterizing what we get, and hopefully every now and then somebody finds one of them useful, and or otherwise it's just registered there. So this is the first one that we characterized, was the Terbium one. Then long way forward, already back in Brazil, we started working on the characterizing the rest of the series of the magnetic rare earths. And then finally, just very recently, when we looked at the non-magnetic rare earths, we discovered a couple new superconductors here. And if there's still enough time, I might talk a little bit about some of the ongoing research that we've been doing as a consequence of these things here. All right, so back to about 15 years ago, I was a fresh new postdoc in Hiroshima University with Professor Takabatake, and one of the topics that I picked up there to look at was to try to work on these rare earth nickel silicon 3 systems. And luckily for me, right, in the very first attempt that I tried to grow a single crystal of this compound, we absolutely didn't know anything about them at the time, and the beautiful crystals just grew right away through the flux method. This crystal here, there's no length scale here, but this is actually the contour of a quartz ampule. So this is a pretty large plate-like crystal that grew immediately. And so then we proceeded to characterize these crystals. First of all, the crystallographic aspects of them, we found out that then these are orthorhombic structure within the CMMM space group. But the A and C lattice parameters are very similar to each other, so these are quasi-tetragonal structure. And there's a layered structure here alternating silicon, nickel, and terbium along the B-axis of the structure. Well, then as we started characterizing this new compound, then what we discovered then is that it turned out to be an antiferromagnetic Kondo lattice, which we could see through several different measurements. For example, right through the resistivity, we can see the signature logarithmic dependence here after a local minimum in the resistivity. It's a highly anisotropic one. You can see here that for the current parallel to B, it's almost like a semiconducting or semi-metallic material up there. Here's the thermal power, also showing very typical characteristics of a terbium that is beginning to fluctuate the valency. What else can I say here? And well, very metallic material. Down here, just Fermi liquid behavior. The magnetization is anisotropic. The z-axis here was found along the b-axis, and when we measure the effective moments, it's very close to the ytterbium expected valency, which means it's very close to +3. In this case, we do see a spin flop here, right at around 1.7 Tesla. And but although the valency is very close to +3, you can see that the saturation moment here at high fields is still quite below what we expect from the interbium moments. So it seems then that's characteristic of a quenched system, right, that is hybridizing with conduction electrons. This can also be seen in the heat capacity, where we can see this really beautiful sharp lambda-like peak at the transition. And by the way, this is actually one of the highest transitions that have ever been found for any ytterbium-based magnetic compound. So it seems like this is a very, although it is a hybridized system, a Kondo lattice, it still has very strong RKKY connections here between the ions. You see that the gamma shows somewhat enhancements, right? So we have a moderate heavy fermion system here. This gives us a Kondo temperature of around 30 Kelvin. And when we calculate the integrated entropy here out of the specific heat, it's still around 60% of our log 2, which then demonstrates that it's really a system that orders in a situation of still having strongly quenched moments here, right? A over gamma square, the Katawaki-Woods ratio is exactly what it should be, which seems like then it's a nice model system to explore different properties related to heavy fermions and coronal lattices in general. So then we started working on some things that we could do at the time, right? So we could apply a little bit of pressure. We didn't have all that much. And then we could see that we basically destroy the Kondo maximum here as we are applying pressure, and we also destroy it as we are applying magnetic field, which seems then that this could be then a tunable system to start searching for quantum critical points. In the particular case of the terbium silicide, the best thing to do would be to look for the magnetic one, so a field-induced quantum critical points. So we did that then later as a collaboration with the people from Ames Lab. And through that characterization, we could indeed come as close as possible into this region here at around 8 Tesla, which is would represent a field-induced quantum critical point. But when we plot the resistivity parameters, right, the rho naught, the A, and the beta parameters here, we see that they don't really deviate that much from what is expected from a Fermi liquid. So it just seems that it's not there, at least coming from this one approach. We couldn't find it over there. And pressure doesn't help in this case because it's just going to make the sample go further away since it's already ordered. When we apply pressure on ytterbium, it just goes further away from the quantum critical point. So what we did then in this case was turn our attention to the germanide, which we expect to have a larger lattice parameter, which would then represent negative pressure. And indeed, when we look at the germanide one, it is a strongly mixed valence system that does not order. So then this one would be an appropriate to look at the pressure-induced quantum criticality. So that's what we did later on, still in Hiroshima. And at that time, then again, we had a limit in this case of about 7 GPa, and so we couldn't quite get to where we would like to, so we can see directly the quantum criticality. But by looking at how the parameters were evolving in this direction, we could make a prediction that this there should be a quantum critical point at around 8 GPa, just a little above where we could go with our instruments. So after that, we were able to interest some people to look at this, some Japanese collaborators, which could go to higher pressures and etc. So the general picture that we get from this is then that if we look at the Doniak phase diagram, we're going to have the typical bell curve of the Doniak phase diagram. Here around 8 GPa, we have supposed quantum critical point. Ytterbium, which has a high nail temperature, should be around here near the maximum. So when we apply pressure, in this case, it goes in this direction. But the nickel germanide should be around here, and with enough pressure then we might go into this region. From here we went on to collaborate with Hitoshi Sato, who was also from Hiroshima but working at the synchrotron, the various synchrotrons labs in Japan. And so with these works, he went over to the synchrotrons labs in order to do some X-ray absorption experiments. Just quick overview of what the type of measurements that they are doing. So the idea here is that you have these ytterbium p states, which if you put in, make some synchrotron radiation inside here with different energies. When we reach an energy of around 8.9 to 9 kilo electron volts, then we enter a resonant condition, for example, for this 2p state, which excites these electrons up into the conduction band. And so one way that we can do these measurements is doing the resonant X-ray absorption, as we see these electrons absorb the synchrotron radiation. And when we compare ytterbium plus 2 with ytterbium plus 3, since the plus 3 has one less electron, the nuclei pull the electron cloud closer down, so we lower the energies, and as a result we can distinguish between the plus 2 and the plus 3 electrons because they peak at different energies. The resonances just come out at different energies here. So that is one way that it was done. When you do this type of absorption, indeed you can see in the germanide that there's a clear signature of both types of ytterbiums. If you work out the average, it should be around 2.5, while the silicide seems to be basically plus 3. We don't really see much of a signature here of the plus 2. But since there was an indication here that there should be some kind of hybridization here, we then went, well, these collaborators, right, went into more detailed experiments here in order to try to solve that. So from the simple absorption spectra, they changed to a technique which is called the partial fluorescence yield X-ray absorption, and the X-ray emission spectra to help out clarify the behavior of the valencies here. So the idea is that instead of just looking at what energies provoke an absorption of energy here, of the radiation, you start looking at the emission here. So in the case of the PFY, you're going to directly look at what is this energy coming out here, of the intensity of the energy coming out. And this energy that's coming out is usually due to the fact that when you excited a 2p electron up here, typically a 3d electron here is going to jump down to 2p. So basically what you did here is transfer a certain amount of energy from the in to the out to your system, right, as it came in like that. And in this case, then you can do the temperature and the pressure dependence on it. So here's an example of what it looks like when you look at the partial fluorescence yield. It does look a lot like the absorption spectra, just because it's basically directly proportional, right? What comes in and what comes out. And in addition to that, then you can do the resonant X-ray emission spectra, which is sweeping the energy that is transferred for each of these incident energies. You sweep the different energy transfers, and you can produce some nice graphs like this that gives you an idea then of where and what energies the resonances come out, right? So when we do that, oops, what happened here? Yeah, okay. So then an interesting thing that I think was actually the first time that they could actually show this very well was that for different systems, you do get different types of responses. And so different techniques can actually be applied to different systems in order to get better resolution on these things. So you can see that the PFY measurement works very well for the ytterbium germanide. You can clearly resolve some very strong peaks here of 2+ and 3+, while the resonant emission spectra doesn't really resolve the +3 aspect here well. So this is not a good technique to study this compound. On the other hand, when you look at the PFY for the silicide, you basically don't see any of the +2 signature. On the other hand, when you go to the RXS, you do see a reasonable peak here for the divalent one, and based on these analysis, then we can get a better precision and show that this is really around 2.5, the effective valency here, while the silicide is around 2.92. There's a very small temperature dependence here. It just varies a little bit as we go from room temperature down to about 8 Kelvin. But in terms of pressure, then we can see some important differences. So when we do the change in the PFY as a function of pressure, you can really see the Terbium 2+ signature going down and the Terbium 3+ signature going up, like this for the Germanide. And then just by fitting all of these as a function of temperature, we can produce and of pressure, we can produce final results like this. So where we were able to stand this far was then to show that as a function of pressure, we can see that the Germanide just increases gradually up to where it comes close to where we expect the quantum critical point to be. And then from then on, well, my collaborators believe that there's a regime crossover here. It doesn't seem that clear to me, but anyway, it seems like from here it just tends to saturate at some lower value, but we couldn't go further beyond that in this case. In the case of the silicide, there's basically no change at all as we just apply the pressure. In this case, it just remains there around 2.92. But the important aspect here in terms of quantum criticality is that we can clearly see in the case of the Germanides that as we reach the quantum critical point, as we cross it, we still have very significant valence fluctuations of the terbium here. And this has implications in terms of the type of quantum criticality that is observed in the system. So consistent with lots of theoretical work that has been put forth over the past decade or so by Piers Coleman, Catherine Pepin, and Qimiao Shi, we can classify, one way of classifying quantum critical points is from those where as we approach the critical point, we do not see together with quantum criticality, a localization of the electrons, and another case where together with the quantum critical point, we see the line of localization reaching the same point. So this represents two classes of quantum critical points. In one of them, as we cross through here, basically we are just doing a reconstruction of the Fermi surface from this normal Fermi liquid state into a spin density wave here, right? So that, and only further on it's going to be localized away from the point. While in this case, we do have what they put forth as a collapse of the Fermi surface, where you have simultaneously a strong change of large Fermi surface to small Fermi surfaces as the 4f electrons leave the Fermi surface, right? And it just becomes a simple antiferromagnet there. So what we could say then in this case is that in our system, this is what's happening, right? In this terbium nickel silicon germanium system. Okay. So this is how far we got in terms of the terbium ones. As we came back from Brazil, rather than continue working in this line, I was actually more interested in keeping a promise that I put in the first paper that I was going to finish characterizing all of the rare earths in the system, right? And this is where my student here, Daisy, comes in, right, Daisy? So she came from Colombia to do a master's thesis, and this is the topic that it was given to her. Continuing from there, we later, postdoc Fabiana Arantes picked up on Daisy's work to complete it. There's actually a massive amount of work here. So I just want to say that this paper is actually, which was published earlier this year, is actually pretty dear to me for several reasons. One of them is, first of all, that among the co-authors we have 6 women and 3 men, and this is something that's pretty rare in our area. I dare you guys to show me a paper that is like that, right, with a vast majority of women publishing in this area. Also, this is the largest paper we've ever published. It's a 21-page paper, and the first one in Physical Review Materials, which is, I think, a very welcome new journal for the area there. So Fabiana, the postdoc, Daisy, and we have lots of collaborators here who did the crystallographic work at UFABC. Well, also Professor Tagabataki helped us with some measurements. And what I'm just going to glide through the 21-page work here, right? So I don't bore you to death. And also I just want to give some due credit where credit is due. So after I worked on the Terbium compound, almost at the end of it, I found out that I was not the first one to actually find this material. There was this Russian language paper published in the Ukrainian Journal of Physics, and it didn't show up in SciFinder or anywhere. It only showed up in a patent search that I was doing for another reason. So, and then I was just diligent and wrote a guy in Ukraine and just said, could you, dig up this paper for me? And he actually found it there. So let me just give proper credit to these guys, right? Gorelenko et al., who in 1977 actually did arc melt these 113 materials and just did a simple magnetic survey of them at high temperatures, just found them paramagnetic, etc., right? So, but they actually showed that this whole system exists. So from here, then we went on to work with the rest of the system. So Daisy started producing the single crystals, right, based on the experiments that we had already gotten from Terbium. She was able then to complete and grow for all of the rare earths, starting from gadolinium all the way up to lutetium. So they don't grow nearly as large or as well as the Terbium case, but they still grew well enough that we could do the magnetic characterization and then move on to the other samples. So as the work was completed, then we could follow how the crystallographic aspects of this series moves on. What we see then is that they start out in gadolinium. It starts out reasonably orthorhombic. There's more or less 1% distortion here between A and C. But then as we move along the series towards Terbium, this really moves strongly into a quasi-tetragonal situation up here. So this is basically 0.1% distortion. So it's basically tetragonal system. And at the same time, we can see that the B-axis starts straightening out. So as it goes from orthorhombic to tetragonal, the lattice also stretches in this direction up here. We could also then orient the crystals and do the orientation dependence characterizations there. So starting out with the typical one that we usually do, right? Gadolinium is usually the most well-behaved rare earth in this case, and it turns out that it's not really the case for this system. Gadolinium in this case is not that well-behaved. We saw some interesting features in this case. For example, for some reason that we still don't know why, you cannot saturate the magnetization of these crystals in any direction of gadolinium. There's actually a metamagnetic transition here, down here, but after that you can see that we are still far away from the saturation moment of gadolinium here, even up to 6 or 7 Tesla, which was the limit that we had in this case. All of these materials turned out to be nice metals, right, with very low resistivities, very high RRRs, which attest the crystallographic quality. From specific heat, we could find out what was the entropy involved in the ordering, which tells us about who is actually participating, right? So in the case of gadolinium, you can see that all of the states of the J equals 7.5 multiplate are there participating in the transition. And in the case of gadolinium, as you usually expect from the half-filled shell, you don't have a lot of anisotropy in the paramagnetic state, but as soon as you transition into the antiferromagnetic state, then there's a clear anisotropy here, which shows what is the favorable direction of the aligned moments. In this case, it's the A axis, which is the preferential aligned moment here. So as we move on to terbium, we basically see the same type of features. Once again, as is typical for terbium, in this case, we see an R log 4 entropy coming out like this, which is the typical ground states that comes out in the orderings of terbium compounds. What else do we have here? And different from gadolinium, of course, here in the paramagnetic state, we already have strong anisotropy, which comes out from spin-orbit coupling and the CF parameters like this, right? So we have a favorable alignment all around the A-axis here, again. And terbium, in the case of terbium, when we look at the magnetic transition, we start seeing multiple steps that are coming out and hysteresis. So these are two features that is kind of surprising. We still don't really know what exactly is being involved here. We do have some suspicions. One of them is that we might have, in this case, issues related to nickel vacancies in the system. And this might be causing these types of hysteresis and also the metamagnetic transitions here. Going on to terbium, if I can change the slide, yeah. So going on to, seems like it's getting slow. No, sorry, going on to dysprosium, we see that now, although the easy axis is still the A-axis, we start lifting up the C-axis also as another possible susceptible direction in this case. We again see the metamagnetic transitions with intermediate steps and hysteresis coming out like this. And if we look here at the transition, there seems to be, although it's kind of hard to see in this case, there seems to be two peaks very close to each other here, so this might actually be a double transition. And we are especially suspicious in this case because as we move on to the next one, which is holmium, then we do see a very clear signature of a double transition in a specific heat. The first one reaches R log 4, and the last one, the second one here, completes the full multiplet of the J equal 8 in this case. And holmium, which is moving in the direction of a shift from the A-axis, easy axis, into the B-axis, which we had seen from terbium. Since holmium is right there in the middle, it actually shows some pretty interesting anomalies here. What we see in this case is that there are two different ordering temperatures. So these two transitions are related to two different Néel temperatures related to two different directions. So when we apply the field along the A-axis, we have a higher Tn around 11, and in the C-axis, along the C-axis, there's a lower Tn. This was actually quite surprising. It's hard to explain how this can happen to have different Tn's. But Fabiana did a search on this, and she ended up finding one precedence for this type of situation here, which was here found in the case of the holmium rhodium 2 silicon 2 system, again showing two different Néel temperatures for two different directions. And the proposal here is that what is happening in this case was known as a component separated magnetic ordering. So it seems that at the higher temperature there's one component of the magnetic moment that orders, but the other one just remains unordered. And then finally at the lower temperature you do get a full ordering of the temperature there. But of course this is just a proposal. This is a conference series paper, so a lot of work needs to be done in order to clarify what exactly is happening in our case, and then maybe help clarify the case of this compound too. So moving on into the erbium system, now we do see a shift from the A-axis into the B-axis. So here's the B-axis susceptibility, which is now higher, but we still have a strong component inside the plane of magnetic response in there. So you can see that this is a very gradual change, right, from completely A-axis happening in gadolinium, then things start happening in a mixture of directions. Here we start getting B-axis, but still with a mixture of directions. We see the same type of features as before, metamagnetic transitions, although no hysteresis is seen in this case. Moving on to thulium, then we start seeing then a very strong easy alignment along the B-axis with very low response from the other directions. And then, as we had already seen previously in terbium, which is the last one in there. It's just fully B-axis with no response from anywhere else in this case, right? So this is what we could follow in terms of the series, how it evolves as we replace the magnetism. Then from here we can just do a lot of trends, and I see how these things follow along the rare earth series. One of the things that we can look at is whether it follows or not the de Gennes scaling. In this case, it clearly does not follow the de Gennes scaling. And one thing that becomes clear in this case is that the gadolinium actually has a very anomalous behavior in the system because it has a lower ordering temperature than terbium. And this is just something that's quite rare. You just don't see that. In general, when you have these magnetic series, gadolinium is always the highest ordering temperature in any case like this. And as we saw previously, right, the fact that it does not saturate when we see the metamagnetic transition shows that there's something really strange still going on with gadolinium that we need to work out. Well, I don't know how 5 minutes. Okay, so in 5 minutes, I'm just going to skip. This is just a summary of all the data that we could gather from characterizing the first characterization of these systems. So let me just move on to having finished all of the magnetic ones. Then we looked at the non-magnetic ones, and as icing on a cake, we were ingratiated with some new superconductors here. This paper was just submitted a couple of weeks ago. Again, I want just to acknowledge Fabiana, who was the postdoc, and Daisy working on that. This was done in Hiroshima as Fabiana went back there together with Takabataki to use the low temperature equipment over there, because since we could go down to 2 Kelvin, we were just using our systems to use the yttrium and lutetium as the non-magnetic references for the magnetic ones, right? And nothing special came out here. But when Fabiana went there and started measuring at low temperatures, then we just could see that just hiding there were just these two new superconductors. And they're not just two new superconductors, but there's some interesting things happening here that are also worth some further looking into. So first of all, notice that we are talking about a ternary intermetallic system, and it turns out, if you look, for example, here in the magnetization curves, that this is clearly a type 1 superconductor. And this is very rare to see type 1 superconductivity in a ternary intermetallic. Type 1 superconductivity is almost exclusive to the elements, right? And then maybe a few compounds here and there. There's probably less than a handful of compounds that are known to have type 1 superconductivity. And here we have 2 of them. So we characterize the yttrium, characterize the lutetium also in the same way. And I'm just going to have to rush here. We have then produced our first tentative phase diagram. These are, superconductivity is killed with very low fields, except when we apply the resistivity perpendicular to the b-axis. Then for some reason also we are not killing the superconductivity as fast as with the other ones, which is also worth looking at. From all of the superconducting parameters, then we can see from, for example, from the coupling parameter here, that these are in the weak coupling regime. As I said, here we can see that they are really type 1 superconductors with low kappa values, and so on. Also, as part of this work, Daisy is working with Jorge in Colombia and did the electronic structure simulations for us. And from the electronic structure, we can see that there are 3 different bands that participate in the Fermi surface and therefore in the production of superconductors here, superconductivity here. 2 hole-like bands and 1 electron-like band like this, both for yttrium and lutetium. The Fermi surface, as you can see, is highly anisotropic with these cylindrical channels along the b-axis, right, which shows that there's almost really no conductance or very little conductance along the b-axis like that. And so this, characterizes these materials as rare cases of a type 1 superconductor, and they are also multiband superconductors in the weak coupling limit there. So since my time is probably basically up, I'm going to skip then all of the ongoing research. Just quickly show this, that we have 2 interesting ones that are almost finished or along a good way. One of them is by making simulations of the rare series in collaboration with a group in Bariloche. So Fabiana has been there a couple of times to do these simulations. And what they are doing, I won't have time to explain all of the details, but using DFT and Monte Carlo simulations here, they are getting quite successful in some cases already in describing the complete transition of these systems with a complete set of CEF parameters that are self-consistent in all of the measurements that we make. So with magnetization versus temperature, the magnetic hysteresis, together with the metamagnetic transition, we can recover the low saturation moment or non-saturation moments of gadolinium in this case, and all with the same sets of parameters, and also a specific heat, which is not shown here. Gadolinium is done. Terbium is also done. We can capture also these intermediate phases here, consistent also with the M versus T curves. So this is coming out well, and still needs to finish with the dysprosium holmium, which is a little more complicated, but it's coming out nicely. And finally, the last one is a collaboration that I've been doing together with Eduardo here, right? So since we are interested in following how the magnetic structure evolves along the series, so Rodolfo, which is one of Eduardo's students, has been doing the synchrotron diffraction experiments on this. They have already solved the gadolinium structure, and just recently also we succeeded with the terbium one, right? Hopefully we will move on to solve all of the structures in this case. And in order to do this, because this system actually has a commensurate magnetic alignment with the lattice, they were very creative in producing a two-step polarization technique which allows to resolve the magnetic peaks when they are buried within the crystallographic peak. And this is also an interesting development that allows us to really see how the magnetic transition develops out in this case. So with that, I just want to finish with the final messages here. So what I could gather from these 15 years working with this system. So in the case of the Terbium system, we have the antiferromagnetic Kondo lattice with supposedly a pressure-induced QCP at 8 GPa. And in this case, the Fermi surface reconstruction probably into a spin density wave. For the intermetallic series, these are highly anisotropic antiferromagnets. We see a gradual shift of the easy axis from A to B as we move along the series. And we have lots and lots of different features here that still require further investigation. For the superconductors, as I said, these are anisotropic 3D metals with a multiband superconducting ground state in the weak coupling regime, and rare cases of the type 1 superconductivity in ternary intermetallics. And all of these compounds, literally all of them, still have a lot of open questions here that we are addressing them both experimentally and theoretically. So thank you for listening to the talk.
All right, I have time for some questions.
If you dilute the system, if you include, say, gadolinium and terbium or yttrium.
In here?
Yeah. Should you get coexistence between magnetism and superconductivity?
Well, we haven't done the gadolinium and terbium yet for this system because we are actually doing it in another system that is actually submitted. Where's Michael? Michael's up there. So Michael has done that, the gadolinium and terbium diluted, but in another system, the zinc 20 system, which came out with some really beautiful results that are right now submitted to PRB, and I think probably should be coming out very soon. In this case, the very first work I did with the very first student was to do the yttrium substitution here and just see what happens. But we didn't have enough time to evolve and actually get results. So this is something that's still, in planning, and I would like to see that. One thing that I was very hopeful and unfortunately didn't seem to work out was to try the solution between germanium and silicon, because I was hoping that by doing that I could actually tune the system straight up to the quantum critical point. But it turns out that they just don't mix When we try to do this type of solution, we end up growing two phases, two separate phases. There's a 216 silicon phase and a 113 germanium phase. So far we weren't successful in this case, which is actually unfortunate, right? Because we still haven't found a way of going right up to the quantum critical point in this case.
Okay, further questions? All right, if not, let's thank our speaker again.
Thank you.
That closed the session.
I saw your UK student, and I'm really and I'm interested in UK, and I know how can I do that in my PhD.
Or you can vote. I'll give you, you can.
Tip?
Yes. Best send me an email.
Yes. Actually, I'm not studying what you are studying. I had my monography in illustration and analysis of some thermodynamic properties of some material, actually some lattice, like square lattice and triangular lattice, but I give up that because my advisor don't work with that, and in my university that is in India.
Oh yeah. I know Uberlandia. Yeah, I have a good friend from Uberlandia, and she's not from physics, but she lives in my city in Cambridge. So no, yeah, Naya.
Have you ever visited?
No, not yet. No, I will come sometime to Uberlandia.
So I attend this my study, but I study this topic magnetic and magnetic.
Yes, yeah.
Not ferromagnetic system.
Yeah.
Magnetic system. And now I'm studying topological layers and perturbation theory. Because Germania didn't have an advisor to guide me in this area.
Yeah,
But
sure.
no problem. I just want to study in UK.
Yeah.
And I don't
So
have,
what you should do is if you send, what do you want to write your email address
Yes.
here? And then you can find me, I can maybe send you some advice in the email. It's the best way. You just put your name and email address. And now you are you're a master's student.
Yes.
I see.
Next year I intend to start
Yeah.
at the end of the year.
Okay. Yeah. Then I see you travelled here for the meeting to Sao Paulo.
Sorry.
Yeah, you travelled here to Sao Paulo for this meeting.
Yes.
Yeah,
Yes.
nice.
It's the first time in São Paulo.
What's
R-
this?
R Maciel
Maciel.
dot 000.
Okay, at gmail.com. Okay, nice. And could you write your name as well?
Yes.
Could you write?
Renan.
Oh, here.
Renan Maciel.
How? What does it say?
RENAN.
Oh, Renan.
Yes.
Renan Maciel. Okay.
Maciel.
Nice. Okay, good.
If you can give me some tip,
Yeah.
or if you can.
You're gonna be. Are you here this week for the tomorrow?
Yes. Until Saturday.
Okay, nice. Okay, good. So
And I think you're gonna be in this week too.
yes, I'll be here. Yeah.
And we can talk if you want
Yeah.
to week.
Sure. Yeah.
So actually, I don't know when I don't know how can I do this study there because I have an idea what scholarship
Yeah.
or some
I can give you some. I can tell you. I can send you an email and tell you what I know about this.
that if you
Of course, always the question is to find funding, to find money. But yeah, I can tell you what I know about this.
okay, or we can talk later.
Yeah, we
along
can
this
talk
week.
again. Yeah.
Thanks.
Okay. Thanks.
Again.
Where were you staying?
20 minutes from here. Oh, my food.
Yeah. Okay. Oh, quite close.
Quite close.
Okay. Okay. Nice. See you around.
See you
Yeah,
tomorrow.
See you tomorrow.